Okay, thank you. So yes, I will speak about KM3Net, focusing on the alert system, taking advantage of the presentation of Sylvia. I don't need to remind you what KM3Net is, and I can directly go to this scheme that shows our online system. So in the online system, we have two, let's say, separated flow that we can consider. The first one is the result of our follow-up of external alert that Sylvia has presented this morning. So I hope you were listening very well, because I will skip that, and I will focus on the release of what I call here internal alert, which basically means that alert that are triggered from our own data analysis. So for this specific internal alert, we have kind of the same scheme, but focusing only on what is interesting there. So you can see that we have the real-time analysis on top here that gives everything to the multi-messenger dispatcher that do all the job for the online job for us. And then we have the two specific flow of ARCA and ORCA. And the idea here is to trying to find interesting neutrino in our data, either from selecting one interesting event in our data or looking for coincidences of several neutrinos in the data. So we'll try to go through all that, all of these modules that are there, trying to give you a hint of what is going on. So I will start with an example of what we could do with ARCA selection. So here I will present a specific selection which is for high energy neutrino. So it starts with a pre-selection of our data, because we have a flow of real-time analysis that gives us a lot of neutrino candidates. The first step is to reduce that in order to remove the atmospheric background. So you can see here an example of the pre-cut selection that we will probably implement in the near future. So you can see some of the parameters that are used to remove this atmospheric background neutrino. So of course you have a physical property and also a construction property that can be used there. That gives us high purity of cosmic neutrino in the end in our sample. And for instance, with this first test, we can reach about 500 events per month with the current detector. So that's the pre-cut, and then among all these events, we need to go below that, because in the end we want to provide to the community few candidates per month or something like that in the scale of per month alerts. So what you can do, it's just an example here of what we can do. So you start with storing a data frame that contains ARCA Monte Carlo simulation of events after the same preselection, of course. And for any real-time neutrino candidate that pass this preselection, what you can do is to compute the number of background events computed in the Monte Carlo that pass a predefined cut in terms of far being computed, integrating over several parameters. So for instance here, I show a graph that gives you two parameters, parameter A and B. And the idea is to compute the number of these background neutrinos that are in this blue region here. And that gives you a far salam rate in terms of number of neutrinos that are able to pass this cut per month. I just wrote there example of parameter that we can use as B and A. The quality of the reconstruction, the track length, or an energy. Those are the main examples that we may use in the future. And then in the end, for any of the event passing this far salam threshold, you need to compute the directional error. And then you have everything for your alert. You have your far and your localization. So that's an example of what we can do with ARCA. Then I can give you an example of what we can do with ORCA. Of course, all strategy can be applied on both detectors, but mostly on ARCA, what we can look for is coincidence of multiplet of neutrinos. So here is an example of how it works. So we are looking for more than one event that is compatible in sky localization and in time. The time window, of course, needs to be defined in your analysis. For the probability of being compatible in time, we can, for instance, use some kind of Poissonian approach that tells you how much it is likely that two events are correlated in time, depending on their time separation. For the probability of the localization, so the probability that they are compatible, so here it's just an example of approach, but if we use a sky map which is pixelized, the idea is that you can simply count the overlap between the two localizations. So here you have a first term, which is the number of pixels that are compatible over the number of pixels that is used, so the union of the both sky map. This is used to weight how much they are compatible together. And you have another term here, which is the number of pixels used, so the union of all that over the total pixel of the sky, and this is this is used to weight the usage over the sky, because of course two very poorly localized events are very likely to be overlapping in the end. So altogether, that gives you an idea of expression that you could use to weight the probability that they are compatible in localization. In the end, you put everything together in a single expression, maybe not with this one, but this is an example of what could be used. And that gives you a quote-unquote p-value that allows you to compute a false alarm rate. And below a given threshold, you can compute the convolve localization. And again, you have everything for your alert, the phare and the localization. Okay, and then the next step in our internal alert system is what we call the Astro module. And I think this is one of the main point of my presentation of today, that has been well presented right before, is the fact that one of the problematic with neutrino alert is the problem that, okay, you have a localization, you have a time of arrival, a probability that this is astrophysics, and basically that's all. And if you are like me, someone trying to do some follow-up, it's not a lot of information. And in particular, when you have restricted time in your telescope, will you follow something that you have absolutely no clues what it is? I don't know. So this is a real problem, I think, for the follow-up. So the idea is that we want to input other astrophysical ingredients in our alert to provide to the scientists clear objective for their observation and clear constraint for their observation. Because again, you don't know if you want to exposure for 1 hour, 10 hours, 1 week, if you want to be fast or not, etc. So the idea is that for every one of our neutrino passing a given phare threshold that we will define, we will try to retrieve all the available public, a lot of available public astrophysical data, so from the catalog to light curve repertory that are available online. So I have here an example of what it could look like. So one of our main focus will be high energy sources and transients, so X-rays and gamma rays, for which we will retrieve source within the given cone of localization of our candidate or our multiplet, trying to find X-ray-like curve to see if there is something brightening at the moment, or known sources like known gamma ray sources. And of course, you can do the same in radio. And for optic, of course, it's a bit different because it's a bit more difficult with the number of sources that you have over the sky. So what we can do is a cross-match with, for instance, a Fink alert system to identify before sending the alert that there is already something that is transient, optical transient there. And you give that to the observer so that they know that they should focus on that when following our KM3Net neutrino candidates. Okay, one word about this last part, which is the alert management. So a lot has been going on there, but it's very preliminary, so I won't give a lot of details on the format and everything. What I can say is that, of course, the minimum thing that we will provide is the false alarm rate and the localization. We will give all that through GCN and the VO event via Kafka. The exact format is still work in progress, as I said, and we have open discussion with IceCube to have a common core scheme for this alert. Yes, so that gives me to my conclusion. So as you can see, there is a lot of steps to make all that, but we have made a lot of progress in the last months and years. Last week, we actually made the first end-to-end test with all steps, at least a portion of all steps already implemented. So things are going quite fast, to be honest. Still, of course, the structure and the topology is under construction, so we cannot give you clear input right now on that. But stay tuned, because the first public alert should come soon, with soon being in few months scale, without being too precise. Thank you.